All right, so welcome back, everyone. So today it's my pleasure to welcome Nicolas Boulle, who will be talking about elliptic PDE learning as probably data efficient. Yeah, thank you.
Yeah, great. So thanks a lot for the introduction and for the invitation to speak in this seminar series. So I'm going to talk about PDE learning today, and this talk will be based on the joint work with my collaborators, Diana Alikias and Alex Johnson from Cornell University. So I'm working in the kind of broad and relatively recent area of scientific machine learning, which basically has been kind of very popular recently, and where researchers in this area tries to essentially combine existing techniques in numerical analysis and the numerical analysis of partial differential equations that have been derived in the past 30 years, and more relatively recent machine learning techniques like deep learning to essentially incorporate both numerical analysis knowledge of PDEs and discretizations and machine learning techniques for incorporating data. And so the aim is essentially to combine those two areas into the broad fields of scientific machine learning to discover mathematical laws and models from data. So there have been quite a lot of recent and successful applications of scientific machine learning in the recent years. So the one that I want to highlight particularly are the ones by a team in DeepMind and another team in Caltech who independently made quite a lot of progress in weather forecasting. And so the aim here is to essentially incorporate both mathematical models for weather forecasting and historical data with a deep learning prediction model in order to essentially forecast the state of the weather in, say, 3 hours, 6 hours, 9 hours. And combining those techniques, they were able essentially to obtain relatively good accuracy in modeling the temperature in the weather with essentially cheaper computational costs than existing numerical techniques. And there have also been some other works in different areas, like the protein folding problem that you have, I guess many of you have heard of by DeepMind again. In another area in materials discovery, and finally in doing numerical simulations. And that's something closer to my research interest, where there's a paper by Raisi, Yazdani, and Kanadakis who employed essentially physics-informed neural networks, so PINs, to simulate fluid flows inside a human body. And so I'm essentially working in the the research area called operator learning. So in my opinion, there are 3 distinct sub areas in the field of scientific machine learning. And so the first one is what we would call PDE solvers, in the sense that you have essentially small amount of data available of your system, but you have lots of prior physics knowledge. So typically you might know, for instance, or you might have a very good prior of the partial differential equations that describe the evolution of your system. And so this is the area where you try to design fast solvers and there are techniques based on machine learning and deep learning. For instance, the physics-informed neural networks PINs fall inside the area of PDE solvers. Another area in scientific machine learning is what we call PDE discovery, where we have some prior knowledge of the system and as well as access to some data regarding the evolution of the system, of the dynamical system that we try to predict. So in this case, for instance, you might have a good idea of the dictionary of terms that exist in your partial differential equation. So you might know that there are some terms that involve the first derivative of the velocity with respect to x, or with respect to time, or with respect to y. And then you try essentially to discover the coefficients in front of those dictionary of terms, in front of those terms. And so this is the area of PDE discoveries. And so there have been quite a lot of techniques proposed by a team from University of Washington, so Nathan Coates or Steve Brunton, that are called Cindy essentially. So they employ sparse recovery techniques to discover those coefficients. And so this is basically this set of techniques are trying to tackle inverse problems because they the type of problems that they try to solve is could be unstable, so they might need regularization to discover those terms. And so finally, the later area is called operator learning, where in this case we don't have we almost have no prior physics background, physics knowledge regarding the systems, but we have lots of data. And so one typical application is that, for instance, you might have the state of the system at a time t, and you try to approximate the operator that maps the state at time t to time t plus delta t. And so this area is called operator learning. So you try to approximate an operator that maps between functions at a given time to other functions. And so contrary to, for instance, PDE solvers area, in this case, there is not really an alternative standard numerical analysis technique for addressing these problems because we don't know what the equation is. So in this case, we don't have much prior physics knowledge. So we try to rediscover the equations, or at least the solution operator that will that corresponds to the solution of the system without the underlying knowledge of the physical laws, just from the data that we have. And so if we are more interested in this area, I've written a survey with Alex Johnson recently on operator learning that you can find on arXiv. So what's our aim in this talk? So our aim is to essentially learn solution operator associated with unknown linear partial differential equations of the form L of u equals F, where L is your partial differential operator. And we aim to do that from observational data. So essentially the data that we have are random forcing terms F, so random source terms F as inputs, and together with that, corresponding solution satisfying the underlying equation describing a system. And I just want to highlight here that we don't aim to address the inverse problem, which will be to discover the partial differential equations from the data, but we try to approximate the solution operator that maps the source terms F to the solution U. And unlike the inverse problems, this is often a well-posed problem where this operator is compact in some sense. And so basically these techniques, so this operator learning areas and this PDE discovery area, I see all of those techniques are kind of complementary. So they will give you essentially different information of the systems. So the PDE discovery one will give you more physics information because the coefficients of the partial differential equation that you discover are kind of written in a human readable form, while the solution operator will give you a fast reduced order model technique for computing new solution to your equation given new source term. And so the main contributions that I will be describing in these talks are first a theoretical result that quantify how much training data, how much training pairs F and U do we need to approximate the solution operator within a given tolerance. And secondly, a practical deep learning technique to learn Green's functions. So Green's functions, so solution operator associated with linear partial differential equations. And the key ideas will be based on essentially standard techniques in numerical analysis that will bring towards this field of operator learning. So first, randomized numerical linear algebra, and then results regarding PDE theory, from PDE theory regarding regularity of Green's functions, and finally a different type of neural networks called rational neural networks based on rational approximation theory. And so before we go into this topic, so I just want to highlight the kind of the standard approaches in the field of operator learning. So as I said before, the aim is to approximate the solution operator of partial differential equations L of u equals F. And so the techniques that are currently existing in the area that have been proposed in the past 5 years are of the following. So first, we generate random functions F, random source terms F, from a Gaussian process distribution. We acquire the underlying solution U, or we measure it from an experimental setup. And then we train a neural network to compute an approximation to this solution operator. And so while this step is usually quite slow, so you have to pay the cost of the training. Once you have trained your network, the idea is that you can then evaluate it at new source term and get a much faster reduced order model than a standard numerical analysis than a standard PDE solver from numerical analysis. But the idea here is that we want to apply this range of techniques in areas where we don't know what the model is. And so the idea is that you can then discover new solution operator or new models that describe your system evolution. And so there have been several deep learning techniques that have been proposed recently. So the first one is a DeepNet by Liu and al, the Fourier neural operator, and the deep green approaches. And so essentially all of those techniques address this problem. And so they're based on deep learning. So they are essentially similar, but they differ based on the type of neural network architecture that they use. And so these techniques aim to, are based on neural operators, which are essentially infinite dimensional generalization of neural networks. So in the sense that they take functions as inputs and output functions instead of taking vectors and outputting vectors. So the DeepNet is based on a branch network and a truncation network. So it's basically performing a low-rank decomposition of the operator. The Fourier neural operator is based on a convolution neural networks and the fast Fourier transform, which is basically a spectral methods for approximating solution operator. And the deep green approach is based on an autoencoder architecture. So there are several challenges in the field of operator learning right now. So the first one is the lack of theoretical results, in the sense that it's very challenging to prove theoretical results regarding operator learning. So while there have been several approaches that try to characterize the approximation power of such the architectures that I've described earlier, we also want to get other theoretical information, theoretical guarantees regarding operator learning, such as the type and the number of training data that we need to train those networks, those neural operators. And this is the topic that I'm trying to address today in this talk, as well as getting some performance guarantees, understanding why certain neural network architectures are better than others and perform better in different type of problems as well. And getting some noise robustness results like uncertainty quantification. And a second challenge that we see is the interpretability of the model. So even if we can get relatively good prediction error with the current approaches, unlike other machine learning models, we don't only want to get good accuracy, we are also concerned about deriving a model that is interpretable, in the sense that here we want to understand the physical laws that describe the system. And so there are also physical properties that we might want to recover from the system, besides just getting a good accuracy in our approach. And so we want either to discover those from the neural network architectures that we train, or enforce those properties by designing a tailored neural network for application. So examples of properties that we might want to recover might be dominant modes, symmetries, conservation laws, as well as singularities, etc. And so in today's talk, I'm going to look at how much training data do we need to learn a partial differential equation. And so to do that, first, I would just want to show you this very simple experiment that I did, where I'm trying to approximate the solution operator of a two-dimensional Poisson equation on a square. So the form delta U equals F. And so what I'm doing here is that I'm basically generating different random source terms F, computing the solution U, and then training different neural operators, as I described earlier, to approximate this solution operator. And so in the x-axis, I'm basically varying the size of my training data set. And in the y-axis, I report the testing error on an independent data set. So each point in this diagram corresponds to another training from scratch of a different neural operator. And so by looking at this diagram, we essentially see two things. So first, we see a very rapid and sharp decay of the error, so an exponential decay of the error in a first part of the diagram, as we increase the size of the training data set, until we basically reach a plateau due to discretization error or optimization error. And so this is kind of very surprising, and this was very surprising in the literature and was noticed in several papers, including the original DeepNet paper, and which is the fact that contrary to most machine learning application, the field of PD learning, or at least this particular example, is what we call data efficient, in the sense that we don't need much training data to achieve relatively good accuracy, in the sense, by relatively good, I mean between 1% and 5% relative error. And so this is something quite surprising, and something that we want to explain theoretically. So why do we need so little training data to approximate solution operator of partial differential equations from data? And so to do that, we are going to look at a simplified model of linear partial differential equations, so the form L of u equals f with homogeneous Dirichlet boundary conditions. And we're going to consider a class of these differential equations for which we know that the solution operator can be written as an integral operator against a Green's function g of x and y. So here g has its function, so it's an object that has twice the dimension of the original partial differential operator, so twice the spatial dimension. And the idea is that this integral operator here is basically the solution operator. So if we know the Green's function, we know basically the solution operator, so we can compute the evaluation at new source terms. So the aim now is to try to approximate this Green's function from data pairs f and u. And so if you first look at the Poisson equation in 1D, so this is what the Green's function look like on the bottom left of this of the slides, and we see two things. So first, we can basically read properties of the original partial differential equation by looking at the Green's function. So the fact that the Green's function is symmetric along the diagonal here is related to the fact that the partial differential operator is self-adjoint. And similarly, we can also read the boundary condition of the equation on the Green's function. So if we look at another example, so here this is the Helmholtz equation with frequency k. So with periodic boundary condition, so we can first read the periodicity of the boundary condition on the vertical side of the Green's function, and the number of stripes that we observe along the diagonal is related to the Helmholtz frequency k. So there are some interesting physical properties that we can read on Green's function and therefore on solution operators. And so now we can move on to our main theoretical result. So we are going to consider elliptic partial differential equations in 3 dimensions in what we call divergence form. So in this form, so minus divergence of a of x grad u equals f, where a here is a coefficient field, a coefficient function with essentially very low regularity conditions. And so we consider this class of partial differential equations. And we know that for this class of PDE, there exists a Green's function g such that the solution operator can be written as u of x equals integral of g times f. And so our main results states that there exists a randomized algorithm that achieves exponential convergence for approximating the Green's function with respect to the number of training data pairs with very high probability of success. So first, why is this a randomized algorithm? So we are going to use random functions f sampled from a Gaussian process to generate our training data. So basically our bounds comes with a certain probability of success coming from the random distribution of the source terms. And the probability that our bounds, so our algorithm converges exponentially, essentially is guaranteed increase exponentially fast as well with the number of training data. So we have also convergence in probability in this sense. And so basically these results kind of give an explanation of why we observed a very fast convergence of the neural operator techniques in the previous slide. So why they can achieve a very fast convergence to the Green's function as we increase to the solution operator as we increase the number of training data pairs. And so with this algorithm, what we try to say, so this is formulated as an existence result, because what we try to say is that the class of elliptic partial differential equations here, in the sense, is data efficient because it has a lot of structure that we can exploit to design fast or data efficient neural operator learning techniques. So this theorem doesn't quantify exactly why the specific neural operator architectures are able to extract the Green's function with a very low amount of training data, but rather said that this class, we can do it. Whether it's kind of an existence statement that says that we can achieve very fast convergence. And when we design neural operator techniques, we should aim to achieve fast convergence, and we should aim to enforce or exploit regularity results, regularity structures on the neural operator architectures. And so while this is an existence statement, the algorithm is actually, the proof is actually constructive. And I'm going to show exactly what the algorithm is in the next couple of slides. And so as you will see, the proof combines core techniques from numerical analysis and applies them and generalize them to infinite dimensions and applies them to the field of operator learning. So we are going to look at randomized singular value decomposition, hierarchical matrices, and peeling, which all come from numerical in algebra. And now we are going to move into the first part of the proof, which is about randomized numerical in algebra. And so if we have a matrix, so we're going to first look at the finite dimensional case and then generalize it to the operator setting. So if we have a matrix A in finite dimensions, so we know that we can write down its singular value decomposition of the form A equals U sigma V star. And from the Eckhart-Jung theorem, we know that the best rank approximation to A is given by the truncation of the singular value to the case singular values. Moreover, the best rank approximation error is given by the tail of the singular values of A. And so there's a landmark result by Alco, Martinson, and Chop about 10 years ago that says that if we have a black box matrix A that we can only sample from random vectors through matrix vector products with random vectors, random Gaussian vectors, then from this matrix we can construct a low rank approximation, so rank K approximation of A from K plus 5 matrix vector products with random input vectors. And moreover, we have these probability bounds that I highlight below, which states that the rank K approximation that we obtain is near optimal in the sense that it's only a square root of K factor worse than the best you can do. So than the best rank K approximation, which is given by the Eckhart-Jung theorem. And this comes with a very, very fine probability of success. And so while this is formulated in simple terms here, I just want to highlight that you don't have to use K plus 5 random vectors. You can actually use any other sampling amount that you want, so K plus P, and you will have different probability bounds, and you can find all of those results in the paper, in the original paper by Alco, Matson, and Chop. And so if we see it in practice, so in black, I've applied I've showed you the best rank K approximation error in the line. So as I increase the number of samples, I'm performing the randomized SVD, and I report the relative error, so in the Frobenius norm. And so in black, this is the best. So this is in black is showing the epsilon K curve, and in blue, this is the result by the randomized SVD. And as you can see, we only get we get essentially a near best rank K approximation to the matrix A. And so this is very useful when you try to approximate very tall and skinny matrix from matrix vector products, in the sense that if your size of the matrix is higher than, let's say, 10,000, dimension 10,000, then you can basically get a faster algorithm than performing the randomized the singular value decomposition, and get at the same time a very good approximation. And so first, our first result is basically to generalize this randomized singular value decomposition algorithm from standard input Gaussian vectors to correlated Gaussian vectors. So the original randomized SVD paper was only formulated with standard Gaussian vectors, so input vectors that have essentially whose entries are independent. And in our work, in our paper, we generalized this theory to allow for correlated Gaussian entries. And you will see later that because we allow for correlated Gaussian entries, This will allow us to basically grow the dimension of the vectors to infinity and apply this result later on to operators and functions. And so this is the theoretical result that we get. So it's basically the same result as the randomized SVD from Malcolm, Martin, and Chop, except that now we can allow for correlated input vectors, and that we have an extra beta k over gamma k factor here that comes from the covariance matrix that we choose. And what we are saying is that essentially you can enforce some prior knowledge of A onto the covariance matrix that you choose to sample your random input vectors, in the sense that if you have already some prior knowledge of the dominant modes of the system, you can enforce that into the covariance matrix, and in some cases get a better approximation than the randomized SVD. And so the right plot is showing an example of this phenomena where I'm normalizing the error by the best Rankine approximation error. So I'm dividing the error by the best Rankine approximation error. So the best you can do is 1 in this setting. And the blue curve is the randomized SVD, while the red curve is the one where I've enforced some prior knowledge on the distribution of the random input functions. And in this case, you can essentially get a better error, like an error that is like sometimes 40% below the one given by the randomized SVD, which can be really interesting in cases where the cost of sampling new vectors is very high, is much larger. The cost of acquiring new data is much larger than the numerical linear algebra cost. And so now that we have this theory, these tools, we can now generalize, go to infinite dimensions and generalize the randomized SVD to approximate solution operators. And so we are going to look at Hilbert-Schmidt operators, which are bounded linear operators between Hilbert spaces with finite Hilbert-Schmidt norm. And basically, Hilbert-Schmidt operators are the right generalization of matrices in infinite dimensions, in the sense that the Hilbert-Schmidt norm of a matrix is a Frobenius norm. And a natural example, one of the most important example of Hilbert-Schmidt operators in infinite dimensions are integral operators. So of the form integral of G times F, where G is the kernel of the Hilbert-Schmidt operator here. And so there are some interesting properties that we can exploit as well. So if we have an integral operator, the HS norm of the operator is the L2 norm of the kernel G. Hilbert-Schmidt operators also have a singular value decomposition. And we also have the Eckart-Jung-Mirsky theorem, which tells us that truncating the SVD gives us the best Rankine approximation in the Hilbert-Schmidt norm. And the error is given by the tail of the singular values up to infinity here, because the operators are acting on infinite dimensional function spaces. And so once we have those tools, we can essentially generalize the randomized SVD from matrices. So from the approximation of a matrix, of a black box matrix A with matrix vector product with random vectors F, all the way to infinite dimensions, where we want to approximate an integral operators by convolutions against random functions F sampled from a Gaussian process. And so in this case, we get essentially a similar result than the finite dimensional one, in the sense that we can approximate the integral kernel G using K+5 random input function F sampled from a Gaussian process with a certain covariance kernel that we choose. And there is also gamma K factor, which tells us that we can enforce some prior knowledge on the covariance kernel from the operator that we try to approximate. So we also basically get a near best Rankine approximation algorithm by using the randomized singular value decomposition on Hilbert-Schmidt operators. And we have also strong probability bounds in this case. Okay, and so this is first, before going into further details, I just want to show you the application of the randomized SVD. So we can basically code this algorithm. And so we can look at this application on a given integral kernel. So this on the top left is the exact kernel that I try to approximate from convolution against random functions. And the bottom one is the one that I approximated or I learned using the randomized SVD. And you can see a very good agreement between those two. And the right diagram now is showing a different choice of the covariance kernel for the distribution of the random functions f. And so in this case, I'm using squared exponential kernel with a length scale parameter L, which I'm varying in these 3 curves here. So the black curve is the best Rankine approximation ever, while the blue, red, and green curves are the result of the randomized SVD with different covariance kernel, so different length scale parameter for approximating this kernel. And so, as you can see, as if I decrease my length scale parameter, I'm essentially able to reach nearly machine precision where I try to approximate the integral kernel here. And so this is a phenomenon that is really understood by our theory in the sense that as I decrease the length scale parameter, I'm able to generate a wider range of random functions. And so in this case, I'm able to compute an approximation to explore more of the action, explore a higher dimensional space on which the integral operator is acting, and therefore computing a more accurate Rankine approximation in this case. So this is something that is really captured in the gamma k factor that appeared in the theorem. And so now that we have this essentially this approximation technique, we can apply it to Green's function. And so we take our Green's function, we apply the randomized SVD to it, so the infinite dimensional randomized SVD. And now we get this probability bound from our series. So basically the direct application of the randomized SVD onto the Green's function. And we just have this epsilon k factor here that, if you recall, depends on the singular values of the Green's function. And so if we understand whether the singular values decay very fast, then we are done and we proved our main theorem. And so the issue that we have here is that the Green's function are not smooth near the diagonal, in the sense that in 3D they can take arbitrary large values, so they can take infinitely large values along the diagonal. And so this basically implies that this epsilon k factor decays very slowly with k. So in particular, it decays algebraically slowly with k. Whereas if we want to prove our main theorem, which is about exponential convergence, we would want epsilon k to decay exponentially fast with k. So we can't use directly the randomized SVD here because we can't compute a good Rankine approximation. So there's no good Rankine approximation that will converge exponentially fast with the Green's function. So we must use the different techniques here to approximate the Green's function. And so this is why we are going to look now at PDE theory results regarding regularity of Green's functions to exploit, to see whether there are further regularity results that we can exploit in our algorithm for approximating them. And so what we're going to exploit is that it's basically a result from Bebedov and Hackbusch in 20 years ago, which states that Green's function have a low-rank structure on well-separated domains. So if we look at this plot, basically what we are saying is that if you take the green and blue domains here, and you consider the Green's function defined on the cross product of these domains, so x cross y, then on these cross products, so the Green's function restricted to these domains have a low-rank structure in the sense that its singular values decays very fast on this cross product. But if the domains are touching each other, like the blue and red domains here, so this is basically part of the domain that lie along the diagonal, then the Green's function here in singular in this case, so we wouldn't find this low-rank structure when the domains touch each other. And so what you need to do here is to employ hierarchical techniques from hierarchical matrices to essentially perform a hierarchical decomposition of your domain in order to partition the domains of the Green's function into green blocks, which are blocks where the Green's function is low rank, so nice sub-blocks in the sense, and red blocks along the diagonal where the Green's function does not have this low rank structure. And so now if we restrict the Green's function to a green block, to a block where the Green's function has a low rank structure, so we know that the Green's function is approximately low rank by Bemendorf and Hackbush, which implies by the Eckart-Chung-Minsky theorem that in singular values decay very fast, are very small, and the tail of the singular values decays very fast as I increase my rank, my approximation rank. And so now we can do that in a hierarchical manner using a technique called peeling, in the sense that we first start at the first level, we partition the domain, we approximate the largest block with the randomized SVD, and then we move on and progressively refine the domains along the diagonal. And in this setting, we can reuse the approximation that we computed in the previous domain to save a number of matrix vector product. And then we work all the way down to the diagonal and compute a low rank approximation on each of the green domain using the randomized singular value decomposition. And once we have done that, we now have to deal with the diagonal, and we are just left with the diagonal to deal with. And so to do that, we are going to exploit the different result, which is the fact that Green's function, even though they take infinitely large values along the diagonal, they are still bounded in the L2 norm, so they are still squared integrable, and they still have therefore some decay as you restrict them along the diagonal. So they have what's called the north diagonal decay. And so this is a different result by Gunther and Widman in 1982, which tells us that Green's function is smooth and has some decay of the diagonal of the form in the form of this uniform bond. So g of xy is bounded by 1 over x minus y. And so this basically tells us that the Green's function decay in the L2 norm as we restrict them to smaller and smaller domains along the diagonal. And so what we are doing is that we do in our hierarchical partition as many levels as we need until the Green's function is very small along the diagonal, so as norm smaller than epsilon. So we can safely neglect it by 0. So what we are doing is on each of the green block, we compute a randomized singular value decomposition approximation, so rank approximation with epsilon error. And then we progress along the diagonal until we can safely approximate, so safely neglect the Green's function and make epsilon error along the diagonal. And if you do all of those techniques, apply all of those techniques, then you get a global approximation to the Green's function that has an overall error of epsilon on the full domain. And so this basically summarizes the proof of our main result, which states that there exists a randomized algorithm that achieves exponential convergence for approximating the Green's function with respect to the amount of training data. And so this characterizes essentially the class of elliptic partial differential operators. So it tells us that we can approximate elliptic partial solution operators associated with elliptic PDEs with a very low amount of data. And the same techniques that I've described earlier extend naturally to other class of PDEs, like time-dependent PDEs, so parabolic partial differential equations, essentially heat type equations of this form with some minor modifications. So you can also apply this range of techniques to other class of PDEs and prove similar type of results as well. And now that we have seen the theoretical part of this talk, we're going to move to a more practical part where we try to exploit the knowledge that we learn about Green's function to design deep learning techniques for approximating Green's functions. And so we are going to look at more deep learning type of applications. So first, we design a deep learning method for approximating Green's function, in the sense that in this case, the aim is to approximate a Green's function associated with linear partial differential equations. So we, contrary to other techniques like the FNO or DeepNet, we focus on linear partial differential equations. So we tackle simpler problems in a sense. But because we understand what type of problems we want to approximate, we can also extract more information, so physical object regarding the problem, like Green's function. So we tackle simpler problems, but we get a more understandable technique. So we extract more information. So this techniques is really complementary to other more advanced neural operator techniques. So what are we doing in this technique? So first, we sample random functions, random source terms f from a Gaussian process with a carefully chosen covariance kernel. Then using those source terms, we can excite the systems, and we can then either perform numerical simulations or do an experiment where we can observe or measure the corresponding solution to these source terms. And we then use them to train our neural networks. So in this case, we write down the loss function in a particular form, in the sense that we train a Green's function neural network that will try to approximate the Green's function, and a homogeneous solution neural network that will capture the boundary conditions. So in the loss function, as you can see, we enforce the Green's function solution integral operator structure in the Green's function, so that instead of learning an infinite dimensional operator that acts on function spaces, we try to approximate an object, functions, a Green's function that takes in 2 inputs and output 1 output. So, and the idea is that once you train these networks, then you can then extract them and visualize them to get some physics, to read some interesting physical features. So what kind of features can you discover? So first, if we look at the Green's function, then we can look at potential symmetries that, as I said before, are related to the fact that the operators might be self-adjoint or not. So they are related to the symmetries of the original differential operators. We can also perform an eigenvalue decomposition and get some information regarding the dominant eigenmodes and eigenvalues of the systems, as well as performing shock and singularity locations detection. And so this later part is supported by the type of neural networks that we use to approximate Green's function. So as I said earlier, Green's function can take arbitrary large values along the diagonal, and therefore it might not be appropriate to use standard neural networks like ReLU neural networks to approximate them. And so to perform this approximation, we use a rational neural network architecture, which are basically standard neural network with trainable rational activation functions. And because we use rational activation functions, they can take arbitrary large values along the diagonal, so they can essentially support the singularity of the Green's function and help us to find where those singularities are located. And we also proved in different papers that these type of networks have very high approximation power, and higher approximation power than ReLU networks, in the sense that they can approximate a similar range of function spaces with fewer trainable parameters. And so now we're going to, before concluding this talk, I just want to show you different applications to differential equations. So in the first application, we're going to consider a simple advection diffusion equation in 1 dimension of this form, where I activate the advection part only on the right half of the domain. So this is this blue term here. So I'm considering this advection diffusion in the interval -1, 1. And the equation is diffusive on the left part of the domain, on the negative part of the domain, and advective on the right part of the domain. And on the bottom, this is the result that I get by training the Green's function neural network. So first, by looking at the Green's function on the left plot, we can discover some interesting behavior of the system. So the fact, for instance, the behavior of the Green's function on the left part of the domain is very similar to a diffusion behavior. So from the Green's function that we obtain from the Poisson equation, for instance. And so this tells us that the system is likely to be diffusive on the left part of the domain. Similarly, on the right type of the domain, the picture that we get is typical from an advection behavior, where the information travels from left to right. Next, in the middle, we plot the homogeneous solution that captures the boundary conditions, and we see a very good agreement between the exact one and the one that is learned by the neural network. And finally, on the right, I'm showing you a picture that is typical from using rational neural networks, in the sense that I'm evaluating the homogeneous solution network on the whole complex plane, so not only on the interval where I train it, and plot its phase portraits. And by looking at the phase portraits and the points where the colors change rapidly, we can essentially see where the poles and the zeros of the rational neural networks are located. And by looking at the poles of the neural networks and how they cluster towards the real line, so towards imaginary of z equals 0, we can, from rational approximation theory, tell that there is essentially singularity at this point, and we can basically, with different change of physics and shocks and singularity location, by looking at how the poles cluster and how far they cluster. So where the pole cluster will tell us where the singularities are, and how far they cluster will tell us what type of singularities are in this case. And finally, in a last example, I just want to show you a slightly more complicated example. So this is a Stokes law in a lead-driven cavity in 2 dimensions. So this is a famous example in computational fluid dynamics. So on the left, I'm showing you the exact homogeneous velocity solution. And the bottom is the one that I learned with the neural network. And finally, on the right, I'm showing kind of with the Green's function here, so different pictures. So I'm showing you what's called now a matrix of Green's function. Because since I'm considering a Stokes law in 2D, I have two differential equations that govern the x and y component of my velocity. And so in this case, I'm trying to map the x and y component of my source term, of my body force source terms f, to the x and y component of the velocity u. And so you can read it essentially as a matrix of Green's function that acts on the x and y component of f and outputs, if you multiply it, as on the x and y component of the corresponding velocity solution. And so we really have a matrix of Green's function here. And the idea is that by looking at the symmetries between the different terms, like on the off diagonal, for instance, and how whether there are symmetries, how the symmetries interact, we can read the properties regarding how the terms are coupled in the original differential equation. We can read some coupling terms here. And so with that, I'll conclude. So in this talk, we described the theory for learning Green's function that give us some indication of why existing neural operator techniques are data efficient, unlike most machine learning applications. This theory is based on a generalization of the randomized SVD to infinite dimension and to operator. And so there's a lot of work to be done in this area to try to exploit and merge knowledge that exists in numerical linear algebra and exploit it to operator learning. So this numerical linear algebra techniques can also give us some information regarding what type of neural operators architectures are better than others, and also how to choose different training data as well. So this kind of theoretical result tell us some information regarding how we should choose the distribution of the source term and which one are more appropriate for different type of physical systems. And finally, I described a deep learning approach, a practical deep learning approach that can approximate Green's functions of linear differential equations. And if you're interested in the latter, there is a package available publicly in TensorFlow that you can download. And so with that, I'll thank you for your attention, and I'm happy to take any question.
Thank you. Any questions? Yeah, okay, there's a question here on the chat. You can unmute yourself, Andy. Andy Gibson, do you want to unmute yourself? There's a question on the chat, Nicolas.
Yes, hi. I was wondering how these operator learning frameworks handle nonlinear PDEs, and if there are any known convergence rates for those, and do you have any ideas for proof techniques there, and also if you've heard of Koopman operator theory and if that might be useful here.
That's it's an excellent question. So so for nonlinear operators, I believe they do not require much string data. So the amount of data you require for training operators associated to nonlinear PDEs are in the order of 1,000 or a few thousands. So it's very far from the millions of images or millions of text corpus or billions of text corpus that you train to learn to approximate to train that you need to train large models. So you don't need much data as well for those equations. And I'm guessing there's also a lot of structure there. So what we exploit really in our theory is really that the solutions, if you look at the solutions at 2 points that are far away, there's a low correlations between 2 points that are far away. So this is this low rank structure. I'm guessing there is also this kind of structure for nonlinear PDEs, but it's a lot harder because you can't exploit any knowledge, any algorithm from numerical in algebra. So you need really completely new techniques for tackling nonlinear PDEs. And as for Koopman,
that's actually why I was wondering if Koopman operator theory might be relevant, because a lot of that is based on SVD and doing these linear algebraic techniques.
That's right. So Koopman is, it's also very interesting. So Koopman, the issue is that it corresponds to ordinary differential equations, Koopman. So you will need a different type of Koopman operator theory for partial differential equations. And so this also might be very challenging to do as well. Because Koopman take in a finite dimensional system and lift it up, but then you will need to take a infinite dimensional system and also lift it up. So it is very interesting, but it requires a lot of new ideas to tackle nonlinear PDEs in this space. Yeah.
Cool. Okay. Thank you.
Leo, do you want to ask your question?
Yeah, I think I already asked on the chat. Is somehow if you, I see that you did this for detail for essentially the elliptic operator.
Yeah.
But then if you have like a hyperbolic operator, like a wave equation, where the singularity structure of the integral kernel is no longer the diagonal, but it could be something much more exotic, more geometrical, shall we say? Then can you still deal with the same way, or is that still open problem for you?
Yeah, so there's actually a paper by Chris Pong and Alex Johnson on 1D wave equation, where the singularity is kind of simple, but it's not along the diagonal anymore. And they apply also, so they also apply the same techniques, but they do, in addition to the same techniques, they do a test for checking whether the green function is low rank. So they can essentially perform a detection of the singularity of the green function. And then when they have detected this, where the singularity is, they can tailor the hierarchical partition to the singularity, essentially.
Right. And so okay, so let me just see if I understand everything correctly, right? So you don't know what the differential operator is to begin with. All you know are solutions or sources and solutions, right? So you don't know what the operator is and a priori figure out where this singularity ought to be.
You can probe your system. So you can select source term, send source terms to your black box system, and detect solutions.
Right.
And from that, you can essentially test where the singularity is along the domain.
In a 1+1 setting.
Exactly. So they have done the 1D setting, the 1D special setting. Anything above 1D is open question, and we don't know whether it's even feasible.
Yeah. Okay. So are you aware that there actually is a theory that restricts how these singularities could look like in higher dimensional? It can't just be anything for the wave equation. It needs to propagate it along a light ray, for example.
Yeah.
And it needs to obey some kind of a Hamiltonian system. Is there any way to be able to incorporate that into your learning algorithm so that it gives you a better chance of finding these singularities in higher dimensions?
Yeah, I was not aware that there were like results that basically characterize those more finely. So if you know any of these kind of results, I'm very happy to chat about those.
I'll contact you by email.
Sounds good,
at some point. Yeah.
Thanks a lot. Yeah.
All right. Other questions?
If nobody else has more questions, I will ask one more, but I'll wait for everybody to ask theirs.
No, please go ahead. I think it's better to ask your questions all at once. Yeah, thank you.
Right. So now, this is sort of going on the inverse problem side, right? So in this sense, for the elliptic equation, your singularity is always going to be in the diagonal, and in that very nice picture, you're able to actually work out where that diagonal singularity is by looking at your source and solution term. Now, I'm going to ask you the inverse question now for the wave equation, right? Because I don't know what these coefficients are, so I don't know where these singularities ought to be. But then if you're able to work out where these singularities are by putting in, sources and probing out, sort of probing solutions, wouldn't you be able to solve the inverse problem of how your original system, which you don't know, which is a black box, ought to propagate these singularities?
Yeah, so it's a great question. So the issue is will still be an inverse problem. So even for elliptic PDEs, right? If we have the Green's function in this case, so it's the nicest setup. Recovering the coefficient is not easy because essentially the map that goes from the Green's function to the coefficients is unstable. And so if we perturb the Green's function slightly, it's not necessarily true that if we perturb the Green's function with some noise, it might not correspond to an existing PDE.
Right.
So we might not be able to recover, or we might be very far off. So the map doesn't satisfy any nice properties, so we might not be able to recover the coefficients even if we have the full Green's function. So we still need some regularization, and it's not clear whether directly solving the inverse problems with the original data might be harder or easier than recovering the Green's function first and then extracting the coefficients. I don't know which one is the easiest one, but in both cases, I imagine you would need regularization.
Right. Yeah. That's a whole. Okay. Yeah.
It's a hard problem in both cases. It doesn't solve the inverse problems. Yeah. Otherwise, the inverse problems would be easy in a sense. It would be like a kind of a contradictory to the inverse problem setup in a sense.
But my question is that if I'm not interested in getting all the coefficients, so for example, in the wave equation, right, the singularity of the kernel of the wave equation, I know from a theoretical point of view that it's the light cone.
Yeah.
Right. Of whatever geometric underlying Lorentzian structure it is.
Yeah.
So if all I'm interested in is recovering the light cone, and I don't really care about the coefficients of this wave equation, I think your method, if you're able to figure out where the singularity of the kernels are, you have a good chance. You can get a nice picture like that.
Or you can also recover some properties regarding the wave speed. So that's something we've tried to do before, and that seems to work quite well. So, but yeah, I'm very happy to chat about it later about that as well. Yeah.
All right, thanks.
Yeah, thanks a lot.
All right, thank you. Any other questions? All right, okay. Thanks a lot. Thank you, Nicolas, and thank you everyone for coming. And see you next week with a few other talks at the end of June. Yeah, thank you. Take care.
Yeah, great. Thanks a lot. Bye.